decarbonization, how it works, and how we can make sure it really is sustainable. Today, we're going to be taking a deeper dive on the raw materials or feedstocks that are the essential building blocks for sustainable aviation fuel. Today, we have three amazing speakers for you to explore how biomass, waste, and residues can be turned into sustainable aviation fuels that deliver significant carbon savings and can earn that label of sustainable. If you have questions during the webinar, we encourage you to use the Q&A function. Our team are there to answer questions, and we'll be putting some of them to the experts at the end of the webinar, time permitting. We have a lot to cover today. And just to have a quick look at the agenda. So first, we're going to be hearing from Dan Lieberman, who is responsible for global sustainability strategy and engagement at Newseed. Newseed are a long-time RSB member and global agriculture innovator holding RSB certification for their Carinata oil seed production in several locations around the world. Dan brings over 2 decades of experience at the climate energy nexus and his expertise comes not just from his role at Newseed, but from many years working in the traditional oil and gas sector. Next, we're going to be exploring how biomass can be turned into SAF via gasification and Fischer-Tropsch process, which you'll hear more about from our speaker, Jeff McDaniel, who joins us from Velocys, another long-term RSB member and committed partner in sustainability. Jeff is VP for new projects and one of the founding members of Velocys, an incredible technology developer who has been transforming the ways that fuel can be made and from what. And then finally, you're going to be hearing from my colleague, Alex Ehrenhuis, who's projects director here at RSB. Alex is an agronomic engineer by training, and during his career has worked in agribusiness to implement social and environmental best practice at the farm level via corporate social responsibility projects. Most recently at RSB, he played a really pivotal role in the revision and update to our best-in-class sustainability principles. And today he's going to be helping us to explore in greater detail what goes into making sure that a raw material is really sustainable. Before we hand over to those experts, I thought it would be helpful to just give a quick refresher on what we learned last week and to give a little bit more context on raw materials. So I have to thank Charlotte Hardenball from Sky Energy, who last week shared this slide. And I think it just gives us a little bit of helpful context that today we're going to be looking at examples of the raw materials that are vital for that HEFA pathway with Dan and Newseed, and then for gasification and Fischer-Tropsch pathway with Jeff and Velocys. And then next week, that mysterious other box, the yellow line at the bottom, is what we'll be covering in our Power to X webinar. Very briefly, I just wanted to illustrate the sheer volume and variety of raw materials which can be considered for SAF and other bioenergy production. The graphics on screen focus only on the US and come from the 2023 billion ton report, which considers feedstock production in the country. It looks at what can be produced according to environmental constraints and includes modeling for projected increases in demand for food, feed, fiber, and conventional products. The reason I'm showing this now is I just wanted to illustrate the huge range of different raw materials available in just a single country that aren't already being used in other uses and won't be, and that can be directed into the bioeconomy. There are hundreds of millions of tons of potential raw materials coming from forestry waste, agriculture, and waste like plastic, paper, and cardboard. This 1.2 billion ton availability from a mature market scenario could be converted to about 60 billion gallons of liquid fuels, and that's about equivalent of 60 billion gallons of SAF. And with global jet fuel demand in 2024 sitting at about 99 billion gallons, you can see that that is a huge potential. Of course, this is just showing that raw material potential. It doesn't consider the big investments in infrastructure, production, and more that would be needed to make that a reality, and also whether all of this raw material can be produced in a way that creates sufficient emission reductions with all the other sustainability factors considered. However, I think it's just kind of helpful to start this webinar with a bit of a snapshot so we can kick off this discussion. And without further ado, I'm going to hand over to my colleague, Dan, to help us deep dive on the amazing feedstocks like Carinata, which can help fuel a sustainable future in flight. So Dan, over to you.
Great, thank you. Let me click on take control. And I'm assuming everybody can hear me. I'll
We hear
Jump
you.
right ahead to the next slide here. Okay, so thank you very much, Hannah. Really appreciate the opportunity to be here. And especially thanks also to Microsoft and to Alaska Airlines for making this whole series possible, which is fantastic. I really enjoyed last week as well. So we heard last week already about what SAF is and the role that it's expected to play into the future. Today, I'll share with you more about the feedstock that we start with. That's the raw material, and it plays a big role in determining the life cycle footprint of the end product. Biofeedstocks are the building blocks of SAF. I'll start specifically on one crop-based source of biomass that Hannah mentioned, which is new seed carinata, and that's within a category of what we call purpose-grown energy crops. I'll take you through a little bit of a story of a seed across its life cycle, and we'll talk about how not all seeds, not all feedstocks are different. They're not all created equal. Some biofuels can be considered sustainable, while other biofuels are not sustainable. And then I'll wrap up with a little bit of the impact indicators, as you see here, how we measure, report, and verify data across the life cycle. So the first thing to know about SAF is that it's essentially the same as conventional fuel. That's why we call it a drop-in replacement. It can be mixed with conventional fuel at virtually any ratio. Some policy constraints and safety-related policy constraints, which are legitimate, do limit the extent to which it can be blended now. But we have had successful flights already, demonstration flights that operate on 100% sustainable aviation fuel. It uses the same supply infrastructure as traditional fuels, doesn't need any modifications to planes or engines. And the feedstocks, the raw materials that we use to produce SAF, comes from a wide variety of sources. And you see a few here, everything from municipal waste and used cooking oil to purpose-grown crops like the ones we're talking about here today. A few examples are carinata, camelina is another one, pennycress or covercress is another, and each has its own story and its own greenhouse gas and environmental footprint associated with it. If you remember one thing from all of this, I think on this slide in particular, you'll see a few different categories of feedstocks. It's that, as I just mentioned already, not all feedstocks are created equal. I was talking to Jeff, who's presenting here with me this morning last week, and he shared, I think, is an excellent thing for us all to remember and repeat, which is that all SAF is good, but not all SAF is the same. Feedstocks come in a lot of different varieties. Phrase that I like to use at New Seed and that I've been saying a lot lately is that how you grow bioenergy matters. And how you grow bioenergy is as much related to policy and the value chain and the value proposition, the business model that works. How you grow all that matters, but how you actually grow the crop on the farm, what you do, the farm management practices and a slew of other aspects across the value chain impact the result in terms of what environmental benefit we have at the end of the day. So our story of a seed, here we go, starts with gathering the robust and transparent data set right here at the site selection level at the individual farm. Before planting occurs, we've already done an assessment of soils, climate, farm management practices, and throughout the fuel's life cycle that you see here on this circle, we're collecting and analyzing data so we can be completely transparent and provide confidence to all the players across this supply chain. All of them need to be considered, the impacts of each and every step along this circle for the contribution to the greenhouse gas footprint and other impacts. So once those sites are validated against the risk of land use change or deforestation, so that we are confident that no land use change has occurred, this is the beginning of what we call a closed loop value chain that we manage as a company. We don't own the entire process, but we manage this cycle and the transparent data associated with this entire cycle. And the reason I mentioned it's closed loop is because we're careful to manage as much as we can within this cycle so that, for example, farmers who sign a contract with us to grow new seed carinata are also obligated to sell that harvested grain back into the same value chain. That's how we are able to remain confident in the sustainability assurance and that the data is accurately tracked across the value chain. So as we follow this seed, and we're looking here from where we are now, go to planting and through the growing cycle, we implement improved management practices. We require the growers to grow in a certain way. As I said, how you grow bioenergy matters. So the farm management practices that improve soil carbon accumulation, improve nutrient retention, growing a cover crop, which we only will grow new seed carinata as a rotational crop in between primary crops so that it's not taking any additional agricultural land, and it's adding as a supplemental source of both revenue and nutrients into the soil to whatever that main crop is, which could be soy, could be corn, could be anything, could be peanuts. When you grow a cover crop, it means less chemical applications necessary, so that improves your GHG. Tillage practices are another big one to consider at harvest time. So now we're going from growing onto the harvest element here. Low tillage, no tillage, that maintains biomass and minimizes carbon loss. And the next sections, processing, transport, shipping, all have GHG emissions associated with them. We're burning fuel, we're using energy. Again, everything that you can measure here is something that we can also manage and optimize. So if we're thinking about shipping, transatlantic shipping, what can we do to improve propulsion systems? What can we do to improve efficiency? All of that contributes. Finally, we've got a proprietary crush process for new seed carinata in particular, and the resulting crude oil is refined, blended, and distributed to customers. In the end, aircraft get to refuel using all the same infrastructure, again, that is already in place. And there we are with the flight and tanks, filling stations, engines, aircraft, all of that remains the same as what we already have in place. So it's also, in the end, I'd say, efficient use of resources in order to achieve all of these environmental benefits while posing the least cost to society in terms of all of those upgrades that would otherwise happen by shifting a lot of that infrastructure. Now, let's go a little, whoops, go back, sorry, here. Am I confused? There we go, okay. Let's go one level deeper. So thinking about how we measure and how we conduct the life cycle analysis. We apply established methodologies, protocols like IPCC, greenhouse gas protocol. These are the 1, 2, 3, 4, 5 main elements that are associated with emissions, both emission savings and releases to the atmosphere of greenhouse gases that include not just CO2, but also methane, nitrous oxide. Cultivation, of course, is energy use primarily. You see here farm equipment use, fuel consumption, same thing with transportation, how we transport. I already gave the maritime example. Processing, again, energy content of the product itself comes into play. The process efficiency, I talked a little bit about our proprietary crush process that plays into that. The fraction of the biomass itself, whether you're talking about a cellulosic biomass or a seed in this case, what part of that is oil? In the case of carinata, it's a very high percentage that contributes to, again, the efficiency of the entire process. Now we have these last two categories. And if you take a look at the chart on the left-hand side, it demonstrates what I'd like for everyone to take it away here is that there are positive emissions or we might think of those as environmental impacts, greenhouse gas emissions that occur. The blue box, the light green box, and whatever, you've got everything above the zero. Now you've got these two additional categories that are below the zero line. So what these impact of these do, just thinking about it as a mathematical formula, you've got positive emissions and you've got negative emissions. Ultimately, what we have is a balance that is approaching nearly, in this case, something that is net zero. And that's where we want to go. So what is this induced land use change and soil carbon accumulation that can provide those negative emissions? Biofuel production. It often takes place on cropland that was previously used for other agriculture. So let's say, for example, you used to grow one thing, now you decide, oh, I am going to start growing soy, and I'm going to grow that soy for the express purpose of producing biofuel. Even though soy is a food crop, and even though that land was previously used to grow wheat or something else that is also a food crop, if that agricultural land is diverted for use in the bioeconomy, as in this example I'm talking through, then we have unfortunately caused indirect land use change. We've extended agricultural land into what was previously, in another case, we could also, let's say, palm oil plantations, very common in Southeast Asia, to see deforestation resulting in order to clear land to create additional agricultural land, additional land to grow crops. There, we've extended agricultural land into what was previously not cropland. That leads to conversion of carbon-rich environments like forests, wetlands, peatlands, and all of that results in the release of carbon from the soils, that would talk about as terrestrial carbon, into the atmosphere. A lot of companies and corporates in their greenhouse gas inventories don't consider land use change in their reporting. Increasingly, GHG protocol is a good example. Many jurisdictions in their regulatory reporting requirements increasingly are requiring the reporting of land use change emissions and indirect land use change emissions as well. Within the GHG protocol, there's a guidance on how to measure and how to report land use change. In California, for example, the California Air Resources Board imposes penalties on crops that cause land use change. So it impacts the carbon intensity score that's associated with that in the LCFS, the low carbon fuel standard in California. In the European Union, under the Renewable Energy Directive, you also have rules that essentially limit the extent to which crops that cause land use change can participate in the market. Finally, okay, the last bit here is agricultural soils have the potential to store carbon and mitigate greenhouse gases in that way. So again, the Greenhouse Gas Protocol has guidance here on how you measure carbon fluxes from land management. And this, I believe that New Seed is among the first, if not the first, to roll out, and right now we are in the process of deploying a global carbon measurement, actual soil carbon sampling and measurement program all over the world, where we have operations to measure over time the accumulation of carbon in the soil. So here, much of this very, very same chart that you've seen on the very right-hand side, you can see the positive and the negative. And this is just a comparison, looking at across a couple of different scenarios. So fossil fuel, of course, looking at that as our baseline, nothing negative associated with that. And we're burning fossil fuels, all of which is releasing GHGs. Look at renewable, a typical renewable fuel such as soy, but which is a food product and does typically displace agricultural land that was traditionally used for food, otherwise used for fuel. You don't have these negative emissions associated with it, or these we'll call them the sequestration emissions, or sinks, associated with it. So this is a good slide to look at that comparison. Now, I think that puts a lot into when you use the word and think about the word net, as in net zero. This is really how to think about that word net and what that means, because in the end, the net is potentially negative or near zero when you're thinking about fuels that also can introduce the land use change benefit and the soil organic carbon benefit. Before I wrap up here, this is just a very broad overview of the benefits that purpose-grown oilseed crops can offer. I've mentioned some of these already: GHG reduction, nutrients uptake in the soils, avoidance of erosion is another one. But all of this also contributes not just to environmental impact, but also economic impact. Think about the improved revenues and the additional source of revenue to farmers that they otherwise would not have during this off-season opportunity. So final slide here. I hope you appreciate that as I've described the data capture, the analysis and reporting that sits behind all of this supply chain is a lot of work, but it enables our assurance program. And it ultimately allows customers to quantify and make very specific claims across a broad spectrum that you see here of impacts: water, soil, land use, social, which also mirrors, if you're familiar with the RSB principles and criteria, all of that demonstration of what is sustainable. And now that we can measure all of these, demonstrate all of these, we can start to have conversations about and provide the assurances that we have gone way beyond just carbon savings. And yeah, we can deliver SAF at a 80% emission reduction, or 90, or even 100% emission reduction or more, but we can also deliver on a whole range of other environmental benefits, like improving livelihoods, for example. So there we go. I hope I haven't gone too far over time, and let me hand it back to Hannah.
Thank you so much, Dan. New Seed is really an amazing example of a company living up to its sustainability ambition. So really fascinating to hear all that goes on in the background. So now, to build on to the story of raw materials, I'm really pleased to hand over to Jeff McDaniel from Velocys to tell us the story of how a solid biomass can go through an incredible metamorphosis to become a sustainable aviation fuel. Over to you, Jeff.
Thanks, Hannah, and thanks to the sponsors of this forum, RSB, Alaska Airlines, and Microsoft. I'm thrilled to be able to share a little bit of our story and hopefully contribute to this discussion on raw materials for SAF production. So for today, I'll start with just one slide on who our company is. I work for Velocys. We are a sustainable fuels technology company, and we're focused on that Fischer-Tropsch pathway that we talked about in the solids to SAF process. We have developed a unique, compact, and highly efficient Fischer-Tropsch technology. I'm based at our manufacturing center near Columbus, Ohio. So if anybody's ever coming through Ohio and wants to see how you make a reactor, happy to host you. We were able to do that with RSB earlier this year, back in February. We are owned, or recently went through a transaction, we're owned by a group of investors who are focused on energy transition and who have deep knowledge in this space and are helping us advance. So that's just a little bit about where we come from. And for clarity, when they talk about the three big buckets of how to make SAF, either liquids to SAF or solids to SAF or electrons to SAF, we're in that solids to, the story I'll share here is around the solids to SAF, and specifically gasification through Fischer-Tropsch. So what does that look like? Well, here are the specific steps. And, for the engineers in the room, we could dwell on this for quite a bit, but I know we have a really broad audience, so I'll spare you all the gory details. I'll just say in all cases, we're starting with a solid residual waste, and that waste could be wood chips, they could be MSW, they could be agricultural residues. It's some type of solid cellulosic material. Now, the way it works out, Mother Nature's made it really hard to convert those sort of materials into SAF. You got to go through a number of steps, and they include sizing the material, separating out, materials that can't be converted. Then you go through a high temperature, they call gasification or syngas generation step to convert the solid material into a gaseous stream. Then we need to remove the impurities, including any biogenic CO2 that's co-produced in the process. And then finally, once you have those gas molecules, that's conditioned syngas, that's where our technology steps in and rebuilds those small molecules into a longer chain molecules or synthetic crude. And finally, we're going to finish it off and go through an upgrading process to produce the finished product. So the same, and while there's different, versions of SAF has been highlighted before, all SAF is fully fungible. And when blended with conventional jet fuel, it is jet fuel. I will highlight one other point in this process, and that if you're separating out the CO2, it does afford you the ability, the opportunity to compress that CO2 and sequester it. And if you're doing that, then you're sequestering biogenic CO2. And that's another pathway for being able to achieve negative carbon intensities and deliver greater carbon savings to the aviation industry. So that's the pathway, and it's just a generic pathway for all, gasification, Fischer-Tropsch processes. Let's talk about the two projects. In addition to being a technology developer, Velocys is developing two projects, one in the UK and one in the US. In the UK, it's our Alto project, and there the feedstock is municipal solid waste. We are currently what we call the FEED, or the final engineering phase, for that project. You can see some of the key parameters in terms of when we expect to operate and the capacities that we'll have. My role is focused on the U.S. project. I lead the development of the biofuels project, and you'll see there again, kind of that we're in a little bit earlier stage, the pre-feed. So unfortunately, I don't have SAF now. We expect to have SAF in the future, and we're showing you how we're going to get there. And I think a key thing about this project is the fact that we can do, that we're doing in a way that will not only use a sustainable feedstock, but a process configuration delivers great carbon savings along with that as part of that SAF. So when we talk about those carbon savings, most of you are probably familiar with carbon intensity scores and how we measure. Just like Dan showed a bar chart for different ways, I'll show how we're able to deliver something that actually has negative carbon intensity and delivers an awful lot of, we will deliver from our project 1.5 million tons of carbon savings per year. And, so if you look at the California baseline, or that's for fossil jet, they show the score there. If we were to run our biorefinery without any carbon capture, we would deliver a 54% reduction. And that's mainly because we're using a biogenic feedstock instead of a fossil feedstock. When we then integrate the biorefinery with carbon capture, that's when we're able to now start to deliver a negative carbon intensity fuel. As I'll show just in a second, when we then add on a renewable power source, which is also coupled with carbon capture, that's where you kind of hit the home run and you deliver the deepest carbon savings possible. So this is a study, this isn't Jeff's imagination. This has been validated by independent engineers and use the carbon GREET model for this basis. So, back to the earlier point, our view is, yes, in general, SAF always delivers carbon savings, but it can vary a lot. And I won't dwell on these, but these are some of the base case examples of how much carbon savings. And this chart, in case you're looking at it, this is the tons of carbon savings you will realize if you purchased 1 million gallons of the fuel. And you can see there's a pretty wide disparity. They're all going to be, give savings. It's just they're not all going to be created equal. So how do we get to that? Just a couple points, and how do we make sure that we're doing this in a way that's sustainable? So let's look a little bit at the project, and just again, kind of where we are is we are at the point where we're in the design phase and development phase, not yet in the construction phase. The general steps there you see are the ones that I talked about. We'll bring in the biomass. A key point here is that what type of biomass you bring really matters. It's essential. So we will be bringing feedstock that has been qualified to both the renewable fuel standard and RSB's certification standard. And I'm going to talk about that in just a minute. But once we have, and those feedstocks, just for, well, what are they? They end up being the tops and the branches from the trees that are large enough for producing lumber, and the thinnings that have to be removed from the plantations, and for the rest of the trees to grow up big and strong and produce lumber. So basically, we're using the types of material from the forest plantations that could never be used for lumber itself. So we're using those essential forestry residues or waste products. We're taking them through the steps that you see there. And it's just some of the key points here is, we do require a fair amount of electricity. So that's why we're sourcing renewable power from our dedicated facility. And we do, in essence, kind of have two outputs. We have the CO2 that we're sequestering in a nearby saline aquifer, so it's permanently put away. And then we will be shipping the product via rail. Our intended market, at least in the early days, is California, since they have a premium structure that is very receptive for SAF and other renewable fuels. Just a quick picture, we have a nearby, this is the power plant itself. As you'll see, what I'll highlight here is this, again, all of the feedstock that's going in are those basically wood chips that are forestry residues, and they will, just like with the biorefinery, be RSB certified. So when we start to talk about the feedstock, then there's two questions that come up for this sort of facility. One, do you have enough of it? And two, how do you make sure that the feedstock you're bringing really is sustainable, is something where you're producing benefits, for the surrounding community and for society at large? So for that first question, we've had a number of evaluations done. If you were to ever come and visit our facility there in Natchez, Mississippi, you would certainly see very quickly like, wow, there's an awful lot of pine trees around here. This is one of the most prolific woody biomass growing regions in the world. So they have extensive privately owned pine plantations. Where we are located used to be one of the largest paper mills in the country that's been closed down for some time. So there's, infrastructure and lots of folks with plantations who would love to be able to supply us with material. But we've gone through the independent study, and we expect that we can have, more than twice as much feedstock being generated on an annual basis as we will need within a 100-mile radius. So all this material will be delivered by trucks on a regular basis. So we're confident that there's enough biomass. So the second question, well, is it a sustainable biomass? And there's several things that we've done there. I'll highlight two of them. One, we have worked with the private firm EcoStrat, who's done their own independent assessment, which was funded by the Natchez community. There's a framework for evaluating various biomass feedstocks that was developed along by EcoStrat and Idaho National Lab. Looks like a whole host of categories in terms of what's the robustness of the supply chain, and can these various sources meet the required standards, because there's a whole host of standards. It's not just the RSB standard, at the international level, but there's the renewable fuel standard in the US at the national level. And then there's the state-specific standards that you have to meet as well. So that's one of the steps that we have taken. You see, we got a AA score, so not quite the AAA, the perfect score, but a really good score, and one that we're proud to be part of. And then importantly, I think the last slide that I'll have here is we have been working closely with RSB quite some time. We had an initial evaluation or audit, and Alex is going to talk about all of the different criteria that get used for any of the certifications that were used. We went through that process now several years ago, and we were deemed as low risk. In other words, there's a low probability that we wouldn't be able to get certified for that. More recently, RSB has come out with a draft standard amendment specifically focused on woody biomass. So there are a whole host of questions like, okay, well, what about the carbon levels in the soil? What about the ability, what about the impacts on various species, etc.? What specific types of woods are being used? So we're the first company that has begun the evaluation and completed a preliminary audit. So we had boots on the ground, as they say, in Natchez, Mississippi, visited 13 different plantations where we might be sourcing woody biomass from. We haven't yet, produced the report, which the basis will provide a public, kind of guidance in terms of how to meet this. And, and to be clear, we didn't get 100%, check marks. There's more work to be done, but I would definitely encourage folks who are considering the use of woody biomass or other solid biomass to work with RSB to begin this process, because what it does, it helps you see like, okay, all right, we got A, B, and C done. Oh, but D, it's going to take a little bit more work. Oh, and E, well, that's going to take a lot of work. We better get after it, begin laying the foundation so that we know as we're ready to move in production, we can have a fully qualified and certified source that's going to be, regularly audited and reviewed and met. So I hope that gives you just a little flavor of the steps that we're taking as kind of a case study for how to ensure that you're delivering a sustainable feedstock. I would echo the themes that there's an awful lot of it out there, and how you gather it and how you validate that you've gathered it and used it in a sustainable manner is a key question that needs to be tackled as you move through the project. So I'll wrap there, let Hannah introduce our final speaker, and be open to any questions there at the end.
Thank you so much, Jeff, for that fantastic presentation. And indeed, it was really special to visit the reactor plant in Ohio back in February, and incredibly inspiring to see the huge investments and technological innovation that you're leading on. So looking forward to seeing the projects that you're working on in the US and the UK come online, unlocking a whole lot of staff capacity. Now, with that, I'm very pleased to hand over to our final speaker, Alex Ehrenhaus, the RSB Projects Director, to dive in a little bit deeper on raw material sustainability. We've also had lots of questions coming in the chat, in the Q&A section. Please feel free to add them in there. Our speakers are going through. Jeff, and that's an invite to you to have a look at them and see what we can answer ahead of the Q&A as well. So thank you, and over to you, Alex.
Thank you, Hannah. Hello, everyone. Very happy to be here, and thank you to our sponsors, Microsoft and Alaska Airlines, for supporting this series of webinars. And I'm going to take the approach from an RSB perspective to highlight a bit more in depth what the challenges, issues, risks, and of course, also benefits of using feedstocks for SAF are. So basically, when you're looking at feedstocks and SAF, you always have associated the greenhouse gas emissions dimension. But it's not only about looking at how there are risks of not being able to comply with regulatory frameworks, but it's also about looking beyond what happens at an ecosystem level with feedstock production. So at a farm level, unsustainable practices could lead to net GHG emissions, of course, clearing land from deforestation, peatland drainage, methane emissions from agriculture, particularly, for example, rice cultivation.
Did we lose Alex?
Oh, yeah, I think we may have.
Sorry, I had a small
Thank you,
break
froze
up
for just
in
a
the
second there.
Sorry, I had a second of breakup in the connection. Sorry. Also, utilizing raw materials with lower life cycle emissions that take food security and land use change into account and implement energy efficient processing can significantly reduce the carbon footprint of SAF production. And it is essential to consider a broad range of environmental and social impacts associated to feedstock production, as I mentioned. So how can feedstock production impact social and environmental outcomes? When you think about a crop, you have a community surrounding the area of production, and you have cultural practices associated not only to how that crop is farmed, but also how the relationship between the production sector and the communities are. And there are several types of issues that one can come across in different types of geographies or realities, including indigenous rights, child labor, land grabbing, land use change, either direct or indirect land use change, biodiversity loss, impacts on soil, etc., etc. So these are very negative aspects associated to feedstock production. But of course, there is a solution. And the challenge is then to be able to supply the demand for food, feed, fuel, fibers, and other needs and materials and elements was not causing negative social and environmental impacts in the context of a still growing population and a growing demand for these types of products. So we could think of these 5 aspects that I'm laying out here: conservation, land use change, soil, water, and food security, as a coin that has it can have both a positive or a negative impact, and that depends on the type of approach to sustainable production that a crop or a feedstock has. For conservation, we saw the case where it has been highly associated in the past that palm oil has a very high potential of deforestation and, of course, indirect land use change and a high level of GHG emissions because of the conversion of native ecosystems into palm plantations. It can also, you can also, however, if you make a robust planning of how to organize a territory, how to organize a landscape, you could target areas that are susceptible, high conservation areas that are sensitive and that require conservation, and optimize the use of that landscape. So conservation can still be achieved together with production. And it is the same for land use change. And with Dan, we just saw a very strong case of where a feedstock such as carinata, as it is a winter cover crop, or it can be used within a double cropping system. So you could include that feedstock for fuel production without causing the necessity to use additional land to replace the land that you need to use to put that crop into production. So with carinata, it's a very strong candidate to mitigate that type of risk. Of course, the risk still persists, and you have to make sure that you implement the you can use, for example, through planning, you can use degraded lands or abandoned lands, and therefore you're actually having a positive impact. But then again, you always have to look at what the industry is using and how to plan the use of this feedstock if you want to source it. And the same goes with soil, water, and food security. Again, carinata is a very good example, but you could optimize through a production system, like, for example, agroforestry. An agroforestry production system could enhance soil fertility, could enhance water retention capacity of the ecosystem, whilst at the same time not putting at risk food security, because you're putting a feedstock that is the main destination or the main use of that feedstock is for fuel production. So this slide here, what I intended to put here is that a sustainable landscape is much more than just a standard that you certify. So if you want to have a really comprehensive approach to a sustainable landscape, a landscape that incorporates the economical constraints, infrastructure aspects, social issues with the population in that landscape, etc., etc. The approach that you have to that landscape must be consistent with that level of complexity and with that level of scale. And that's why I included, as an example only, you could have an approach of working on a policy approach at a landscape level. For example, if it's a landscape that still has illegal deforestation, you could work on the policy framework of how that legal framework is not being effectively implemented, and you could tackle that issue. Producer support, if you know that the potential for increasing the yields at a farmer level is still has a big gap that you could cover. Therefore, there is an opportunity to work with farmers to support them to increase their yields, and of course work on other aspects like what type of practices does the whole producing community do at a farm level and which aren't being implemented that could be looked at as a solution to cover any of the sustainability risk that landscape might have. And of course, with financial incentives, the same, and market alignment would also be included here. And so a standard is a mechanism that works at a farm level and at a supply chain level. And RSB has a standard, but has many more activities and covers much more services than only the standard. So basically, the message here is that when you look at a landscape, it's not only about a standard, and RSB has many tools that go beyond a certification approach that can be explored together with any partner. And this one is to the contrary of the landscape. This is focusing on the standard in itself as a tool, right? So what is a standard? A standard tries to cover the three typical pillars of sustainability: the environmental, the social, and the economic pillars. And they're basically statements about how things are supposed to be done. And that's why I organized it in a structure like a pyramid, where in the case, for example, of the RSB standard for principles and criteria, which is the standard that operates at a farm level per excellence, you have one standard, but you have 12 principles, which are subdivided into 39 criteria associated to these 12 principles. And then it's detailed through the requirements, where who wishes to certify with a standard needs to demonstrate with evidence to that specific requirement. And that's where the major challenges of a standard come to light, when you need to translate what the requirement in the standard is asking for and how you're able to demonstrate that you're complying with that standard. Of course, you usually have an audit to ensure that this is being complied with. You have different approaches. It can be a self-declaration, self-audit, or you could do it through a third-party mechanism, such as RSB. In this case, you guarantee objectivity and you ensure that there is no conflict of interest during the audits. So basically, as you can see, through application of a standard which is adapted to the context, for example, in the RSB standard for principle and criteria, there is a very unique principle, which is food security. That principle is context specific. So that means that you have to do a diagnosis based on what is happening, not only on your farm or on your several farms or your sourcing network, but how that sourcing network impacts the communities that are being affected by that activity. So you with a standard, you go beyond a farm level. You're able to ensure that feedstocks are sustainably produced. You can reduce the risk of fossil depletion, as I've given some examples of. And of course, you can contribute to climate change by implementing all these measures. So again, here, this is an issue of scope in the RSB standard system. So in our case, sustainability is relevant for all SAF raw materials. And this means that the certification covers primary biomass feedstocks and also waste residue feedstocks, including from bio-based and non-bio-based materials like recycled carbon. And again here, why is the RSB standard robust? Because it covers a lot of different principles that range from legal aspects to, as I mentioned, food security, water, soil, and land. So this standard in particular is very comprehensive. And as I mentioned, food security is very interesting because you need to reach out into communities, create baselines, and if you detect the risk of food security, you need to mitigate that risk and potentially through your planning, through your actions, create more food than for the communities than before the operation was there. In conservation, of course, we have a very comprehensive list of references that are inside the standard that you need to check out. And we have different tools that support you in navigating which these frameworks are, which references are. But again, this also includes in this principle stakeholder consultation, because this enables you to mitigate the risk that you might have not seen a relevant area for conservation that you should have to look at. And finally, in water, it's about operations not depleting the sources of water of the surrounding communities. So as I'm a little bit out of time and running through these last slides a little bit faster. And additionally, there is the low ILOC risk biomass module from RSB. It's a voluntary module, but you can attach it to the audit and certification system. And it's a module that enables you to ensure that you haven't created indirect land use change through displacing different activities. And last but not least, I think Dan also raised the point about claims. Of course, any standard and certification system has also specific procedures to guarantee that these claims can be made and what type of claims can be made. And that's it for me. I rushed the end a little bit, Hannah, so we could finish in time. Sorry.
Thanks so much, Alex. So we've had quite a lot of questions come in, and I know that we're at the top of the hour. Dan has already been going through in the Q&A and responding to some of those that were addressed to him. So thank you, Dan. If people are happy to hang on for just a couple more minutes, Jeff, I have a few for you that have come through. If you are able to just hang on for 2-3 more minutes. So we have a question that's come in from Fabian saying, how many megawatts does it take to produce 1 liter of SAF through Fischer-Tropsch? I'm not sure if there's one single answer to that, but maybe you could give us an overview of how you get to a figure.
Yeah, so no, there's not a specific number. What I would say when it talks about I don't know if we publicly disclose the size of our facility or not. Be happy to answer those directly for those who are interested. But I do say you do need a fair amount of power. You need power to run the air separation plant, syngas compressors. If you're also doing for this, since we're moving the CO2 via pipeline, that has to be compressed. So, it would, so it's, it varies depending on how you configure the plant. So it's certainly not one size fits all. But maybe the other point I'll say is, so everybody who does their carbon intensity calculation does account for, well, how much renewable power input do you have, how much energy are you using to move the product, move the feedstock, etc. So that's really the beauty of the life cycle analysis, that it factors into all that and, shall we say, motivates folks to use the most, least amount of energy or the most renewable source of power for all of those components as they move ahead.
Thanks, Jeff. And then there's two more questions for you. What I'm just going to start with. So for do your feedstocks need to comply with specific specifications from purity or contamination point of view before they go into the Fischer-Tropsch process?
Yes. So for any, I'd say for any, broadly speaking, any chemical conversion process, there's going to be specifications on what you can feed into it. And for those any catalyst chemists out there will know that the Fischer-Tropsch reaction itself is particularly sensitive to sulfur and a whole range of other compounds. So we have specifications both on the feedstock, which broadly, it's pine chips, so, of a certain size, so the tight specs aren't there. Where we deal with, shall we say, various impurities is in the process itself. So that syngas cleaning process is where we will remove the sulfur and other impurities. So it's analogous to, I think, many other ways for producing SAF.
Thanks so much, Jeff. And then finally, once fuel has been produced, what specifications does it need to be tested against before it can be blended? So is there a specific ASTM standard is that different to the HEFA pathway?
Yeah. So drawing a blank on the number, but there's an ASTM specification that defines the requirements for each of the different pathways. So there's a Fischer-Tropsch pathway, there's a HEFA pathway, there's an ATJ pathway. I think there's a total of like 7 pathways that are currently approved. The key point is once you've, met the requirements for your pathway, then your product, your SAF, can be blended, anywhere from 10 to more commonly up to 50% with conventional jet fuel. And at that time, you basically have conventional jet fuel in terms of all functionality, performance, ability to store and use.
Brilliant. Thank you so much, Jeff. Going back into the Q&A, we had some brilliant questions for for Dan earlier on, and he's been kind enough to go and answer them just by typing, but we had some questions around the rationale for supporting the difference in the CI for carinata using wheat or canola area, and he's explained that in some detail. So if you're interested, I really encourage you to go and have a look in there. There's a lot of references. And with that, I'm going to wrap up and just remind you to please register for the final 2 webinars in our series for SAF Now. You will be finding us at the same time, same place. So 5 p.m. Europe, 8 a.m. Pacific, 11 a.m. Eastern Time. As a reminder, all of these webinars are being recorded. You'll be able to catch this one next week on our website. There's a section for the recordings. And yeah, we look forward to seeing you as we cover and dive into Power-to-X and Book and Claim. You can access the registration links using the QR. And I would really like to give huge thanks to, of course, our partners, Alaska and Microsoft, but really on this one to Dan, to Jeff, to Alex for your wonderful insights in the webinar. And of course, to everyone who's joined us, and especially those of you who have given us a little bit more time than we had promised to take from you. So thank you so much for your attention. And looking forward to seeing you next week.
Thank you. Thank you, Hannah. Bye.
Thank you. Cheers. Bye-bye, everyone.